In number 9, Carlos thinks he has made a significant discovery and has discovered a new variation of monarch butterflies. Now, what he notices is he takes 4 traditional butterflies and 4 of the new butterflies, and he measures the difference in their wingspan. So he finds that when he does the mean difference from the 4 new butterflies to the 4 traditional butterflies, he finds that the difference in their mean wingspan is 0.5 of a centimeter. Now, what this question is asking us to do is we want to determine whether he has made a significant discovery. We want to figure out, using a 95% confidence level, whether the mean difference discovered by Carlos was of statistical significance or not, whether it just occurred by chance. Okay, so in order to do this, Carlos did a re-randomization of 70 resamples of the butterflies. And the dot plot here shows the outcome of this. So what we want to first do is we want to figure out where the mean difference from the 4 new butterflies he measured as compared to the 4 traditional butterflies he measured lies on this dot plot. So he wound up with a mean difference of 0.5, and we could see 0.5 lies right here on our dot plot. So we want to look at values as extreme as 0.5, as well as anything even more extreme than 0.5, and we want to figure out what percent of the distribution this makes up. All right, so let's count the dots. So we have 1, 2, 3, 4, 5, 6, 7 dots. Now that's 7 out of, there's 70 dots here altogether. So 7 out of 70 is 10%, right? 0.1. So what we can say here is, this is a usual occurrence. It occurs within the 95% confidence interval. So unfortunately, Carlos has not made a significant discovery. All right, this is what I wrote. I said, the mean difference discovered by Carlos is not statistically significant. A mean difference of 0.5 or higher, see right here, not right there, right here, occurs approximately 10% of the time, which is well within the 95% confidence interval. And just a side note, in order to prove that something is statistically significant, you want to prove that it occurs less than 2.5% of the time. Because if this in here is the middle 95% of our information, then the outer 2.5 and 2.5 that fall out here add up to make that remaining 5%. So in number 10, Elizabeth had to wait for 6 minutes at the drive-thru at her favorite fast food restaurant, and she was upset about this, so she notified the manager, and the manager assured her experience was unusual and would not happen again. So a study was done by this restaurant that found results that were approximately normal, and they found the mean wait time to be 226 seconds and the standard deviation to be 38 seconds. So what we want to do is we want to figure out, using a 95% confidence interval, whether her wait time was unusual. Now, when you're using a 95% level of confidence, what we're really doing is we're just seeing what falls within 2 standard deviations of the mean. All right, now first thing, she had to wait for 6 minutes. Now the data they give us is within seconds. So if we want to figure out how many seconds 6 minutes is equal to, well, just multiply it by 60. 60 seconds in a minute, right? So that means there's 360 seconds in 6 minutes. I know there's one of 2 ways you can go about showing your work. First of all, since they told us that, the results of their study were approximately normal, we can actually just draw out the normal distribution curve if you want. You can kind of draw one of these out, and we could say, well, here's our mean. This bar represents 1 standard deviation above the mean, and this bar represents 2 standard deviations above the mean. We're also going to have to go 2 standard deviations below the mean. We're going to have to go in the negative direction as well, because keep in mind, if you want to use a 95% level of confidence, it means you're within 2 standard deviations of the mean. So 2 standard deviations below the mean, all the way up until 2 standard deviations above the mean. All right, so they told us the mean wait time was 226 seconds, so I'll put that on the mean. And since the standard deviation was 38 seconds, if we add 38 seconds to 226, that'll give us 1 standard deviation above the mean to be 264 seconds. Now, if we add in another standard deviation of 38 seconds, that'll bring us to 302 seconds. All right, now let's go below the mean. So if we subtract a standard deviation of 38 from the mean, that'll bring us to 188. And if we subtract off another standard deviation from the mean, that'll bring us down to 150. So what this shows us is that the normal, we're using a 95% confidence interval. The normal wait time lies somewhere in between 150 and 302 seconds. So no, Elizabeth's wait time definitely did not fall within the 95% confidence interval. So the manager was right. The other way you could show your work here, if you didn't want to draw this out, you could just really say that if we want to find the interval is going to be equal to the mean plus and minus 2 standard deviations, so 2 times the standard deviation. So the mean is 226. We're going to add to that as well as subtract from that 2 times the standard deviation, which is 38. So it's going to be 226 plus and minus. 2 times 38 is just 76. So you first always want to subtract, right? You want to find the lower bound of your interval. So if you do 226 minus 76, I'll just kind of do that over here. 226 minus 76, that gives us 150. And then if we do 226 plus 2 standard deviations, so plus 76, that gives us 302. So that again tells us that her wait time, or that, I'm sorry, the usual wait time should be somewhere between 150 seconds and 302 seconds. So now we could just say, I mean, you have to write this out, but using a 95% confidence interval, normal wait time should be between 150 and 302 seconds. Since 360 is outside of this range, Elizabeth's wait time was unusual. Number 11 says a population of bacteria doubles every 20 minutes. There are currently 100 bacteria in a petri dish. How many bacteria will there be in 4 hours? All right, so since it's doubling, it's growing by 100% every 20 minutes, so we're going to use our exponential growth formula. All right, so there's our exponential growth formula. Now, we're looking for how many there will be after 4 hours. So we're looking for the A. We're looking for the ending amount after a certain time period. So I'm just going to bring down the A. And the P is the initial. So we started with 100 bacteria, so we can replace that with a 100. All right, now here our rate, since it's doubling, it's growing really by 100%. The rate is 100%. So if you took 100% and change it to a decimal, you'd have to move the decimal place back twice, so it really just becomes the number 1.00, or just 1. And that's how we get its doubling, right? 1 plus 1 is 2. Now, we're not going to raise it to the 4th power just because it says 4 hours. T is really the number of time periods we're talking about here, and it tells us that the population of bacteria doubles every 20 minutes. So if it doubles every 20 minutes, within an hour, 3 time periods have passed, right? 20 minutes plus 20 minutes plus 20 minutes. 3 of those make up 1 hour. So really, we want to take the amount of time periods in 1 hour and multiply that by 4, because we're talking about a 4-hour period. So altogether, 12 20-minute periods have passed in 4 hours. So we're going to raise this to the 12th power. Again, in 4 hours, there will have been a total of 12 20-minute periods, right? Because there's 3 20-minute periods in 1 hour. So 4 hours have passed, so 3 times 4 is equal to 12. All right, so all you have to do is just figure out what this is equal to. So I'm just going to rewrite this as 100 times 2 to the 12th power, and you can just plug that in your calculator, and when you do, it gives you 409,600, and I'm going to label that bacteria. So that's how many bacteria are present at the end of the 4th hour. Now, another way you could have done this is really just by listing out how many bacteria you would have at the end of each 20-minute time period. So, for example, okay, if you guys remember from Algebra 1, right, sequences and series, right, you could say that initially you start off with 100 bacteria. So I would say A sub 0, right, my initial amount after 0 hours here is 100. Now, after the first hour, after the first 20-minute period, I could rewrite that as A sub 1. I would just take this number right here and double it. I would have 200. So I actually listed all these out. I'm just going to kind of move that over and show you all. But after the first 20-minute period, right, if you take 100 and double it, you get 200. After the next 20-minute period, we say that A sub 2, you would double this again and get 400. After the next 20-minute period, A sub 3, you would double this again and get 800. So this is really how much you would have at the end of the first hour. And if you kept going, this would be at the end of the second hour, third hour, and fourth hour. So I mean, either way, you still are getting the same answer. This way you just have a lot more to list out, but here you would have the same thing at the end of the fourth hour. You'd wind up with 409,600 bacteria. Number 12 deals with half-life, so we're going to use our half-life formula right here. So let me just quickly go over what everything refers to here. So this Y on the left-hand side of the equation is the amount of the substance that remains after T time. This Y sub 0 right here just refers to the initial amount of the substance. K is our decay constant, and T is the time that it takes, the half-life time. Now, E, just remember, E is a constant, okay? It's approximately 2.718. All right, so based on what they give us, they tell us the half-life is approximately 6.44 days. A patient is injected with 18 milligrams, and they want us to determine to the nearest day the amount of time that it would take for the patient's body to have only 4 milligrams left in it. Okay, so, in order to determine T, the amount of time, we would have to know what K is, the decay constant. And unfortunately, we don't know that. So let's take a look at what they give us and see if we could first solve for K, and then we could maybe use that to help us determine how long it'll take for the patient's body to have approximately 4 milligrams left in it. All right, so if we use our formula here, all right, let me just write that out. So we have Y equals Y sub 0 times E to the KT power. All right, well, let's just say the patient is injected with 18 milligrams. So I'm going to replace this initial amount with an 18. Bring over the E. Here we're solving for the K. We don't know what the decay constant is. Now, they do tell us that the half-life is approximately 6.44 days, so I can plug that in for the time. So what that means is that's how much time it takes for the substance to only have half of whatever you started with. So here, if we started with 18 milligrams, half of that would be 9 milligrams. So I'm going to replace that for the Y. That's how much of the substance would remain after this half-life of 6.44 days. All right, so let's just solve this. Divide both sides by 18. 9 divided by 18 is 1/2, or 0.5. And that leaves us with E to the 6.44 K power. All right, so now we know to get rid of an E, we can put ln in front of both sides of the equation. And what's going to happen is these are going to cancel, so it's going to leave me with ln of 0.5 equals 6.44 K. And to get the K by itself, just divide both sides by 6.44. All right, now I'm actually going to write out the whole entire value of that. I'm not going to round too early. I mean, you could round to nearest 4 decimal places. Usually with a decay constant, I just write out the whole number, because then when we go to substitute it into the next part, it just makes our answer that much more exact. So this right here is what K is equal to. Okay, now that we've found K, what we can do is we can determine how much time has passed until there's only 4 milligrams remaining. So if we go back to the formula, we're going to substitute the left-hand side of the equation with 4, because that's the amount we want remaining. We started off with 18 grams, so we could replace the Y sub 0 with 18. Now we know what the K is, so I'm going to write that whole entire number for K, so negative 0.107 and so on. And I'm going to bring the T down. This is what we're solving for. All right, so let's just solve really the same way. Divide both sides by 18. 4/18 simplifies to 2/9. I'm going to leave it as a fraction because as a decimal it just keeps repeating. So these 18s cancel off and it leaves us with e to our power that we have here. Now again, we know to get rid of an e, what we would do is we would put ln in front of both sides of the equation. I'm actually just going to squeeze it in right here and here to save some room. So that leaves us with ln of 2/9 equals, these cancel, so I'm left with negative this whole big decimal right here, times t. And to get t by itself, just divide both sides by this decimal. Okay, so in your calculator you can just plug in ln of 2/9 divided by that decimal. And when you do, it gives you approximately 13.9743, and they want it rounded to the nearest day, so we're going to wind up with 14 days.